So continue on our exploration of getting used to triple integrals. Let's look at an evaluation problem. So here let's suppose that a block of conducting material is defined by the same region as our previous example, right? The same bounds, 0 to 1 for x, 0 to 2 for y, 0 to 3 for z. And we say that due to heating conditions of the block's boundaries, the temperature of this block can be modeled using the function f of x, y, z is equal to 200 times x times y times sine of pi z degrees Celsius. And we are asked here to find the block's temperature over this region. So we want to start here by setting up the triple integral. So we still have this integral, this triple integral over that solid region D of the function f of x, y, z dv. And the bounds are still the same. You can use your favorite order here. So I have 0 to 1 for x. I'll let my middle integral be 0 to 2 for y. And the inner integral is z 0 to 3. And at this time, we have a temperature function described by 200 x, y, sine of pi z. And make sure we have enough room. And the order is dz, dy, dx. All right. So we're ready now to go ahead and evaluate. So we can either keep this as one integral or separate it out into 3 pieces based off of the variables. So what I can do is pull this 200 out to the front since it's just a constant. And now I'm going to separate the integral based on the bounds and the variables. So the outer integral is x. So identifying the x in our function, we can think about this as 200 multiplied by the integral from 0 to 1 x dx multiplied by, now identifying the y variable within our function, we can think of this as being multiplied, and I'll use brackets here, big parentheses instead, because the dot product is not far away. And the middle integral here is y, so that's 0 to 2, y dy. And then, last but not least, we have z. So our bounds on z are 0 to 3, sine of pi z. So we can think of this as being multiplied by the integral from 0 to 3, sine of pi z dz. And now we're ready to evaluate each one of these integrals. So we'll do this out piece by piece just to keep things clean. I have the x integral from 0 to 1, x dx. So this is x squared by 2 from 0 to 1, which leaves us with 1/2. We have the y integral from 0 to 2 of y dy. So this becomes y squared all over 2, evaluate from 0 to 2. So we end up with, 1/2 multiplied by 4 minus 0, which gives us 2. And last but not least, we have the z bounds. That's z has the bound 0 to 3 of sine of pi z dz, which integrates to minus cosine of pi z by pi from 0 to 3, and I'm going to pull out that minus 1 by pi, and we have cosine of 3 pi minus cosine of 0, and we of course know that cosine of 3 pi goes to minus 1, cosine of 0 goes to 1, so this leaves us with negative 1 over pi multiplied by minus 1 minus 1, so minus 2. So the two negatives cancel each other out, and we are left with positive 2 over pi. And so we have the 3 values here. We have 1/2, 2, and 2 by pi. Just don't forget here when you plug them back in, don't forget about that 200 out in front. So plugging everything in, we have 200 multiplied by 1/2 multiplied by 2 multiplied by 2 by pi. And we have some nice cancellation here. The 2's cancel each other out, leaving us with a beautiful final answer of 400 pi degrees Celsius.